Let's do a quick review of the steps that occurred in that method of substitution. We're going to define a new function or variable w, and it's going to be something that you see in the integral in most cases. And in most classic substitution examples, you'll also see somewhere else in the integral the derivative of that w. That's usually a cue as to what to choose for your w factor. Then we're going to find the relationship between w's and x's in the derivative sense by differentiating. And we're going to write it in the form of dx equals some stuff times dw, because dx is in our original integral. And then we try to rewrite the integral using only w and dw. Get rid of all x's, because we can't have mixed variables running around. Then there's a self-check. If you can evaluate the integral, then that's good. What you did, this substitution and the work involved, traded one integral you didn't know how to do for a better one that you can evaluate. If it turns out, on the other hand, that you still have x's left and you can't get rid of them, or you got something more complicated than your original, then that's a cue that you should probably try a different substitution or a different technique, like some of the ones covered later in the course. Let's take a look at an example here. Find the integral of tan of x. Well, that's a bit of a problem because there's only one function and we don't see something and its derivative in its current form. So one of the general guidelines when this happens is to try to rewrite the integral into a new form if you can. And one of the ways we can rewrite tan of x, of course, is sine of x over cos of x. Okay, now we start to see some potential. The derivative of cos is sine, and well, again, up to positive and negative values and up to constants, but the derivative of sine is also cos. So which one should we pick? Well, remember the earlier example, we're always going to end up dividing by the derivative of our w. And so if I can divide by the derivative, I'm going to want to let w be the cosine, because then I'll be able to differentiate by sine, or divide by sine rather, and that'll cancel out the sines. If I choose the cos, I'll divide by cos, but then I'll have 1 over cos squared. That's less useful. We'll do an exploration later on with an example where we try both methods and see how bad it goes. For this one, we'll just do it in the most direct way possible. We're going to pick w equal to cos. As soon as we pick that, then we know the derivative relationship will be negative sine of x, the relationship between dw and dx, and we're going to do the same thing we did before, bring the dx up, the negative sign down, and so negative 1 over sine of x dw equals dx. Again, think small changes. So the original integral, sine of x over cos of x dx, is equal to, let's replace piece by piece. Sine we left where it was. The cos of x is now our w. Let's put that in a box here, highlight it. So our w is cos of x, so we can change the bottom for w, and the dx is equal to negative 1 over sine of x dw. And it is important to keep these d's around. I know some people think, they're just these little placeholders. Remember, they actually represent small changes in x or small changes in this new variable w. So they are relevant. Okay. And our substitution did what we hoped. Notice that we get to cancel out the sine of x's here. And so we get a negative sign, integral of 1 over w dw. And that's so much simpler. And there's no x's, just as important. So it's a much simpler integral. There's no x's. We can actually evaluate this integral with no difficulty whatsoever. It's negative ln, careful here, absolute value of w plus a constant. So here we actually integrate. Up till then we were just doing manipulations. Now we actually do the integral, and then last but not least we go back to x's. And w is cos of x. Sorry, go back to x's. And this is our conversion to the original variables again. So back to our original x's, and we're done. That is the antiderivative of tan of x. Are we sure? Let's take a look at the next page. It's not usually requested or specified in most test questions or exams, but remember, it's an easy check. To do antiderivatives are complicated and hard. Why not do the little bit of work at the end to make sure you have the right answer? So if we're going to verify that what we have is the right answer, pardon me, we have negative ln cos of x, absolute value, plus c. And the question we're asking is the derivative of that equal to simply tan of x? If it is, then we have the right antiderivative. Well, let's find out. It's equal to, for sure, negative, the derivative of ln is 1 over cos of x, and then the derivative of the inside function is going to be the derivative of cos, which is negative sine of x. And the derivative of the c, of course, is 0. And in fact, that does give us negative and negative is positive, sine of x over cos of x, and that, in fact, equals tan of x. And so, yes, indeed, we get the same value here as we had before. The integral of tan of x is this, because the derivative of this is tan of x. Just a quick little note as a sideline here. Just remember that when we take the derivative of ln of the absolute value of x, that equals 1 over x with no absolute values. We did it the other way around, finding the integral of this, but it applies equally in reverse. There is an absolute value in ln, but when we differentiate it, the sign of x actually matters here, and so we get the 1 over x without the absolute values. So that's a second example of how we can use substitutions and check them to evaluate somewhat more complicated integrals.